Defining sine and cosine as the x and y coordinates of the point on the unit circle that corresponds to the angle theta inevitably involves the building of what we call a reference triangle, a right-angled triangle that involves the x-coordinate, the y-coordinate of the point on the circle, as well as the hypotenuse, which in this case is 1 because it's built within a unit circle. However, if we, for example, increase our circle and think about the point on the bigger circle, we can notice that the scaling of the triangles, because they're going to be similar triangles, actually preserves the ratios. So instead, sine and cosine can be defined as ratios within this triangle. Cosine, being the x-coordinate, can be defined as the ratio between x and 1, and sine can be defined as the ratio between y and 1. That way, when the radius of a triangle grows, this will preserve the ratios between the actual triangles. So let's write this down. So in our picture here, cosine can be defined as x over 1, and sine can be thought of as y over 1, which will, of course, then generalize to cosine of the angle in the triangle being defined as the ratio of adjacent side to the hypotenuse. For the sine, we're going to have opposite side to the hypotenuse. And then we can derive the rest of the trigonometric functions respectively. So for example, tangent will then be opposite of hypotenuse because it is a sine over cosine, and therefore I can actually take these ratios and simplify it from there. Now, thinking in terms of the triangle also invokes some properties of the triangles themselves. So for example, remember that the angles, the interior angles of the triangle all have to add up to 180 or pi radians. This angle here is the right angle, which is 90 degrees. Together with this theta, that means that the remaining angle has to have the measure of 90 degrees or pi over 2 minus theta. Now let's take a look at sine theta and cosine of pi over 2 minus theta. Okay, so sine theta of this angle right here is opposite of a hypotenuse, so y over 1. Cosine of pi over 2 minus theta is the cosine of this angle, which is adjacent of a hypotenuse, so also y over 1, which means that these two values are actually the same. And that will be true always, in that the sine and the cosine are actually shifts of one another by pi by 2. Think back to the graphs of sine and cosine. It's the exact same sinusoidal curve, just a little bit shifted off. Okay, so it's nothing but a phase shift to get from sine to cosine, and it's actually easier to see from the triangle than from the unit circle itself. Now, given these definitions of trigonometric functions as ratios is very useful when we actually have to compute things within given triangles and in various applications. So let's say we have this triangle here and we're trying to compute the values of sine of alpha, tangent of alpha, and secant of alpha, where alpha is one of the angles. So for the sine of alpha, we're going to have opposite over hypotenuse, and in this case, the opposite of alpha is side of length 8, and the hypotenuse is going to be 17. So sine is 8 over 17. Cosine of alpha is going to be adjacent over hypotenuse. From the perspective of alpha, adjacent side to it is 15 and hypotenuse is 17. Finally, tangent of alpha is going to be opposite over adjacent. So again, from the perspective of alpha, opposite is 8, adjacent is 15, so tangent of alpha must be 8 over 15. Notice that all of the properties that we've defined before must also hold for the definition of sine, cosine, and other trigonometric functions within the triangle. So for example, we still must have that sine squared plus cosine squared is 1, and of course the tangent is actually sine over cosine. All of these properties will hold true no matter what. Now, we can be asked questions, these are very popular questions to ask. Given some information within the triangle, determine the rest of the information. So in this case, we're given that this angle is 30 degrees and the length of this side is 7, and we're asked to compute the lengths of sides A and C. There are a number of ways to do this, and I will talk through just a couple of them. First of all, you could solve for the third angle here, because this is 90, this is 30. This angle has to add up to 180 with all of them, so this angle actually has to be 60 degrees, and we see that this is in fact one of the special triangles. So you could, instead of involving trigonometric functions, use similar triangles, with the special triangle being just a smaller version of this one, and then talk about ratios of sides. We're going to take a different approach here and think about actually using the above definitions of trigonometric functions to help us with computations. So for example, let's apply the definition of sine to this angle of 30. So sine of 30 degrees is going to be opposite side over hypotenuse. So it's going to be 7 over c. Now, sine of 30 degrees, I know from special triangles or otherwise, is equal to 1/2, which now means that 1/2 has to equal to 7 over c. So let me write this out separately. Solving for c here, I will get that c is equal to 14. So I can replace the c with 14 here. Now, I can solve for a using a similar technique, and maybe I can look from the perspective of the 30-degree angle here and notice that to solve for a, I can involve the adjacent with either the hypotenuse, which would mean the cosine function, or the opposite, which will mean the tangent function. I can also, at this point, utilize the Pythagoras theorem, because I know the lengths of two sides and I'm only looking for the length of the third one. In fact, using two of the methods is probably better, because this will allow you to double check your answer. Let me go the cosine way. I know that cosine of 30 degrees is √3/2. That's the value that comes from one of the special angles. But from the picture here, from the perspective of 30 degrees, cosine is adjacent to the hypotenuse. So it's going to be a over 14. And so I have an equation, √3/2 is equal to a over 14. And solving for a, I will get 7√3 after some cancellation. Again, I encourage you to actually try other methods and maybe do the exact same computations from the perspective of the 60-degree angle here to ensure that you actually get the same answers. Okay, let me put this on as the answer here too. Finally, trigonometry, especially triangle trigonometry, is indeed very useful in various types of computations. This is one of the standard ones. We're going to look for the height of the tree. So there's a person that walks 30 feet away from the tree, and she measures an angle of elevation between the line of sight to the top of the tree and the ground at 57 degrees. As shown in this picture. We would like to find the height of the tree. So what we're after is this height of the tree right here. Okay, so taking a look at the picture, we have the angle, we know the length of the adjacent side to the angle, and we want to know something about the opposite side. So the sides that are involved from the perspective of the 57-degree angle that we know the measure of is adjacent, and opposite. So now you have to ask yourself a question: what trigonometric function involves adjacent side that we know to be 30 feet and opposite, which we are trying to compute, so height of the tree, h. The trigonometric function that involves both of those is, of course, tangent. So we can compute tangent of 57 degrees, and we know that to be the opposite over adjacent, so h over 30. Now, we can actually compute the tangent of 57 degrees as something on our calculator. So here, we simply have to solve for h. It will be 30 times tangent of 57 degrees, and plugging this into the calculator will give you approximate value of 46.2 feet. Okay, so oftentimes in the word problems, all that it comes down to is being able to set up the correct corresponding trigonometric function for a really straightforward calculation. Please take a look at Module 6b on WebWork, as well as a bunch more exercises on the next page to deal with looking for various measurements within the triangle, some more complicated than the ones that we've just covered, but based on the exact same idea, as well as various word problems.